Hello, everyone, and welcome to today's Microsoft's Intro to Azure Quantum workshop. This workshop follows really nicely from yesterday's, so feel free to check out the recording of that if you haven't done so already. The Microsoft Azure Quantum Platform is a next-generation solution for connecting hardware backends from multiple providers with software and optimization tools through a single cloud service. During today's tutorial, please post any questions you have in the chat, and we will stop periodically to answer them.
It's great to welcome Maria back to QC Hack as our speaker today. Maria Mikhailova is a principal software engineer at Microsoft Quantum, focusing on education and developer outreach. Maria is the author and maintainer of the Quantum Catalyst project, an open source collection of hands-on tutorials and exercises for learning quantum computing using the Microsoft Quantum Development Kit, and the organizer of Q Coding Contest series. She is also a part-time lecturer at Northeastern University, Seattle, teaching Introduction to Quantum Computing and the author of the O'Reilly book, Q Pocket Guide. Please join me in welcoming Maria.
Thank you for the introduction, Sarah. Hello, everybody, and it's great to be talking to you today again. Today, I'm going to pick up pretty much where I left off yesterday. Yesterday, I introduced you to the basics of quantum computing and at the same time, the basics of C# programming language and some of the tools in the quantum development kit we use for working with this language. Today, I'm going to focus on the next step in this logical sequence, the quantum software development workflow, and how you can use a variety of tools in Microsoft Quantum Development Kit and Azure Quantum to support all the steps of this workflow. So this talk ideally would prepare you for the challenge we are going to offer to you on Saturday. So we will be really focusing on Azure Quantum tools. So I'm not going to be introducing any quantum computing topics, and I might cover one or two C# concepts, but not deeply. For slightly more detail on today's agenda, I'll start with just a couple of slides, a lot fewer than yesterday, giving you the overview of the components in Microsoft Quantum Development Kit and the quantum software development workflow. After that, it's going to be 100% demos. I'll show you the end-to-end process of writing and evaluating programs using C# and QDK tools. And then we will spend a fair bit of time familiarizing yourself with Azure Quantum so that when you get to the challenge of the hackathon, you have something to start you there. Let's see. So Microsoft Quantum Development Kit. It's, as the title subtly suggests, a collection of tools for developing quantum programs and working with them. So simulating them, evaluating them, testing them, all that kind of things. One of the core components of Quantum Development Kit is C# programming language, the main specific language for expressing quantum algorithms. You have seen bits and pieces of it yesterday already, and today I will show you a lot more. C# is integrated with development tools that you likely have used already for other programming languages, such as Visual Studio if you're a Windows developer, Visual Studio Code if you're not, or even if you are, and Jupyter Notebooks. Next, there is a collection of tools for simulating quantum programs. As we will see later today, we don't want to write a quantum program and run it immediately on a quantum device. Quantum devices are a rare resource, and they are noisy, and they are intermediate scale NISQ, which means they're not going to be able to run a lot of our programs that we want to work with. That's where the simulators come handy. And the last component is the libraries and quantum katas. The libraries implement a lot of common patterns used in quantum programs, such as quantum Fourier transform. It's not a primitive you want to write by hand yourself every time. It's just asking for extra bugs in your programs. So libraries provide that kind of primitives. And the quantum katas are a collection of programming tutorials that help you learn quantum computing by solving quantum programming problems. I showed you some of the quantum katas yesterday, and I'm not going to be spending time on them today. However nice they are, we're going to focus on slightly a different aspect today. A quantum development kit is cross-platform and open source and free to use. Somebody asked in yesterday's workshop if it is free to use. The answer is most definitely yes. And as for quantum software development workflow, the thing we need to consider about quantum programs is that very few of them are quantum only. So if you're running, for example, Deutsch or Deutsch-JAWS algorithm, like we did in the yesterday's workshop, you can get away by writing only the quantum component of your program and nothing else on top of it. But if your quantum application is slightly more complicated, like the one we will see today, using Grover search to solve a problem, it is more and more likely that it's going to need to interact with classical software. For example, for preparing inputs, taking inputs from the user, for example, the query as some kind of description of the problem you're trying to solve, and converting it into a format that Q# program can handle, or generally quantum program. Or on the other hand, take the results from the quantum program and convert them into a human readable format, or perform some later steps of processing it. For example, Simon's algorithm, if you're familiar with it, includes the classical component running the quantum component multiple times to get this series of bit strings. And then it converts these bit strings into a system of linear equations and solves them classically to get the final result. So this kind of algorithms requires integration of quantum and classical components. This kind of algorithms is called hybrid algorithms. And this is what quantum programs predominantly are. They're hybrid. With this in mind, here is what our quantum software development process is going to look like. We start with identifying the problem, figuring out the algorithm that is good for solving it, which is not actually on the slide because this happens on the whiteboard, pen and paper, without actual QDK support. But then you go and do steps that require various QDK components. You start by writing the quantum code, the quantum part of your solution. You can do this using Q# and the tools for integrating it with various editors, like I mentioned already, or you can do it using other quantum programming languages. I will show you today how Azure Quantum supports running jobs using Qiskit and Cirq. So you can basically take existing code in one of those languages, tweak it a tiny little bit, and run it on Azure Quantum. So you need a quantum programming language, not necessarily a specific quantum programming language. Now, next, your quantum programming language is going to come with libraries. The logic in this step is very similar to what you do with classical software development, actually. These days, very few people write code in assembly or assembly-like languages. We all want to write high-level code. When we add up two numbers, for example, we don't want to think about how our CPU stores them. Are they little endian or big endian? How are negative numbers stored? We just want to write C equals A plus B and move on to something actually interesting. Something that is solving the problem, not figuring out the exact circuit level behavior of each step of the implementation. So this is what the libraries in Quantum Development Kit aim to do: provide you with standard patterns and leave you with more brain power to focus on the actual algorithms you're trying to implement. Next step, once you have your quantum code written, you need to integrate it with classical software. C# can be integrated with either Python or .NET family of languages, C#, F#. I've tried it with Visual Basic.NET. I wouldn't recommend you to do this, but I have tried it. And later today, I will show you how it works with both of them. Well, not Visual Basic.NET, C# and Python. Next, once you have your code written, you want to make sure that it is reasonably correct. It is a huge pain to debug code once it runs on hardware, because if you got incorrect result, it's a lot harder to figure out whether it's incorrect because of noise or because your logic is actually incorrect. So as far as possible, you want to use simulators and run the code in simulation on the small instances of the problem that simulators can handle, or to use specialized simulators to see that your code is correct. In this part, there is also writing unit tests for your code. I'm going to show you later today. But basically, if we're talking about quantum software development, you want to borrow as many techniques from classical software development as possible. And writing unit tests for code is an old and tried technique that it kind of, there is no reason not to use it. Now, after you have figured out that your code is correct, or at least done enough to convince yourself that it is, the next step before submitting it on hardware is figuring out whether it is going to actually fit within the limitations of the quantum device. Constraints such as the number of qubits required by your program or the depth of the circuit that is required all inform you whether you can actually run this program on hardware or whether it will either not fit or be overtaken by noise a long time before you get a useful result. For this, we have resource estimators, a tool that doesn't simulate the program, but it goes through it and counts various gates and qubit allocations and deallocations. To give you the statistics of the resources it takes to run this program and let you figure out whether you can fit it on a hardware device or not. And finally, the last step is, once you have convinced yourself that your program is both correct and is going to fit within the constraints of the quantum device, you can run your program on quantum hardware via Azure Quantum. And at this point, I'm going to switch away from the slides and spend the rest of today in demos. And this is a good point to make a little pause and take questions if there are any.
Yes, the first question is, we have a participant who is learning Q# and quantum algorithms through doing the quantum katas, and they're wondering if it's desirable to open GitHub issues if they spot any issues with the exercises.
Yes, absolutely. That's a very nice side effect of events. It's quite possible that there are issues still. In fact, after they were first released, I found kind of a very obvious issue a year after they were released. So yes, absolutely. I actually already got one issue on the repository yesterday, which may or may not come from this event. I might not answer it immediately. I'm a little busy this week with the hackathon, but I will absolutely appreciate it and get to it eventually.
There's one more question. They're asking, will the warm-up challenges require Azure or will it just be a free-form challenge?
There's going to be both. We're going to have warm-up challenges, kind of to make sure that the participants are prepared to the basics. And then there's going to be a free-form challenge. I think that worked really nicely last year, the combination of small warm-up challenges and then the main one. So we're going to try to do it again.
There's one more question. It says, in terms of Qiskit being allowed to be used for the hackathon, is Q# preferred or is it indifferent?
We're not going to score based on the language you used. The scoring is going to be based on other things. So the warm-up challenges may or may not require a specific language to do them, but they're going to be very simple. Like it's not going to require you any of the finer points of any languages involved in the warm-up challenges, just the basics. I'm trying not to give away too many spoilers here. Is that it for the questions?
There are a couple more, but we're going to ask for some clarification. So I think it's good for you to continue.
Okay, sounds good. Again, I'm going to do a lot of demos for each of those steps. So if something is not making sense now, hopefully it will make sense in 10 minutes or 20 minutes. Okay, let's see. Here I'm looking at a project that solves a very simple problem that is too embarrassingly simple to be solving it using quantum programming, but I still do because it's a good educational example. The problem it solves is solving a modular equation. We have three parameters, integer parameters, A, B, and C. And we're trying to find a solution to the modular equation A times X plus B modulo C equals 0. The first component of this solution is the quantum code that solves it. I'm working in Visual Studio here because I'm on Windows. My Linux machine has Visual Studio Code set up. But showing you both in one session would be a bit of an overkill. And I'm using Grover Search to solve this problem. So the main components of the Grover Search solution are, of course, the marking oracle, and then the standard pieces of Grover Search. So you can see an operation that is that implements phase kickback trick, converts a marking oracle into a phase oracle by allocating an extra qubit and applying the sequence of gates to it. Next, there is the preparation of equal superposition of all states in our search space. A lot of Grover Search implementations just prepare a superposition of all basis states and work with more complicated oracles that check whether the specific state is in the search space or not. But in our case, it's a lot easier to build this check in the equal superposition preparation. And then there is the operation that runs Grover Search. So given the marking oracle and the search space size, and the operation that prepares the average, the superposition of all search space states, it basically prepares an equal superposition of search space states and then runs Grover iterations for the given number of iterations. And then there is one more operation that interacts with the classical code. So effectively, it's the entry point of this code. It takes the parameters A, B, and C from the classical code. It instantiates the marking oracle and the preparation of the superposition and the number of iterations, calls the standard Grover search, and returns the measurement results. Now, one thing to call out here quickly is that generally speaking, modular arithmetic is not a trivial thing to implement on a quantum computer. But fortunately, I didn't have to do it for this demo. Instead, I'm using library operations. A Microsoft Quantum Arithmetic namespace offers a lot of arithmetic, in particular modular arithmetic, performed on quantum integers. So I can call basically two library operations and be done with modular multiplication and addition. Very convenient. And then the within apply construct, I usually get a question about it if I skip it, implements the conjugation pattern. A lot of quantum computing algorithms use the pattern in which you apply a unitary, then another unitary, and then the adjoint of the first unitary. This is, for example, the uncomputation pattern. If you perform some computations, then read out the result, and then you undo those computations. Very often found in quantum oracles, for example, which is what we're looking at right now. Within apply is a Q-sharp language construct that implements this pattern automatically. So it performs this block of statements, followed by this block of statements, and then the adjoint of this block. So it uncomputes the within block at the end of its execution. Very convenient. And another library operation I'm using here is arbitrary state preparation. Preparing an equal superposition of all basis states is very easy. It's all Hadamard gates. If you want to prepare a superposition of a different subset of basis states, you need to be a little clever about this. And again, here there is a library operation that doesn't need you to think about it in great detail. Instead, you provide the array of amplitudes of those basis states that you want to prepare, and it does the state preparation for you. And this is effectively our quantum code. Okay, of course, I forgot to ask our hosts to share the link. This demo, if you want to follow along reading it, or if you want to explore it later, it's going to have a lot of useful components in it, is on GitHub. This link, tcnicholas/demo, used in one of our workshops. If you folks could share the link with the Twitch stream watchers, it will be great. I know folks always ask for the notebooks later when it comes to the Azure Quantum submission part of the demo. So there it is. Okay, so for now, I covered the first two steps of the quantum software development workflow, writing the code and using libraries in it. The next step is integrating it with the classical code. For now, I'm going to show you how to do it with C# while we are still in the Visual Studio environment. Later, when we switch to Jupyter Notebooks, I'm going to show you how to integrate it with Python. This way, I cover both languages in slightly different environments. Here is our C# code that solves a problem that is that pretends to be more user-oriented than just solving a modular equation. So the problem I have here is, let's say we're looking for a book which has an ISBN number, but one of the digits of this number is missing. And we want to recover this digit before we go and look for the book. So we imagine that a user provided this query, the digits of the ISBN number, except one that is missing. And then our classical code is going to do the classical preprocessing part. ISBN numbers use the checksum mechanism, which means that if one digit is missing, the number becomes a modular equation that can be solved to recover this digit. If there are two digits missing, you cannot recover them that easily. You get a list of candidates, basically. But here we have just one digit missing. So our classical preprocessing is going to take our input query and perform some simple computations to figure out our A, B, and C coefficients of the equation. And then it hands off those coefficients to the quantum solution. How it does that? It creates a simulator on which it's going to run this program. Quantum simulator is a quantum development kit full state simulator, also known as state vector simulator in other terminologies. So it just does the straightforward simulation of the system state. And then you submit the code to this simulator by using the name of the operation that is the entry point, this last operation, which is exposed as a C# class to the C# compiler. And it uses its .run method, providing it the right simulator as the first parameter and providing it the rest of the parameters as integers. And the result here is the array of measurement results. And after this, the classical code takes reins again, and it converts the measurement results that are effectively a bit-by-bit notation of the integer and converts it into an actual integer. And then the final step is printing the recovered ISBN. Let's see how this application works. Now you run it the same way you would run any .NET application here by pressing F5, or if you run from Visual Studio Code or command line, you use .NET Run, and it builds all the components and produces the result. You see that it got a correct equation here. It figured out that it needs to use 2 iterations of Grover search to solve it, and it prints the recovered ISBN. And this ISBN is a bit of an Easter egg that I think I already gave away, but this is a book we all know and love. Also, I'm not sure you can actually get it for 59 cents. I definitely paid more for mine. And this shows us the first 4 steps of the process, from writing the quantum code to running it on a simulator to make sure that it is correct. In the next step, I'm going to show you how to write unit tests for this code. And then we will switch to the next steps of the software development process, evaluating this program and running it on hardware. Any questions so far that are not going to be covered later?
Yes, we have a few questions. The first question is about the nature of Q#, and is Q# more like Lisp or like object-oriented programming?
Well, it's definitely not like Lisp. It doesn't have nowhere near enough round brackets, which is a good thing. It's also not object-oriented programming because it doesn't have actual objects. Also, it is tempting to say that it is sometimes. If we need to call out a paradigm that it is, it's a combination of like regular procedural programming and functional programming. So you can write your code using the normal flow control constructs like for loops and if statements and operations that are effectively just procedures. But you also can do convenient functional style things like using operations and functions as parameters for other operations and storing operations in variables, that kind of thing. So it has been mostly inspired by F# and Python, I think, bits of C#, of course, but it's really a thing of its own. Plus, it has a lot of quantum computing constructs that you're not going to find in Lisp. For example, it allows you to generate adjoint and controlled variants of an operation automatically. It has some quantum specific structures built into it to help you express quantum algorithms. So it has a lot of features, really, and I wouldn't say that it's similar to any single one language.
Great, thank you so much. And a follow-up to that question was, does this imply that Q# is more strongly typed functional as opposed to void and static lexical statements? For example, are people allowed to save qubits in a JSON file, such as in Haskell?
It's definitely strongly typed. Like you cannot do implicit casts, for example, from integer to long or to double. You need to do them explicitly. Once a variable is defined to be of a specific type, it remains of that type. I'm not sure I caught the second part of the question, the clarification.
Yes, the second part of the question was, are we allowed to save qubits in a JSON file, such as in Haskell? So I'm presuming the state of the qubit.
Yeah, that's a good question. So Q# considers qubits something that only exists within one run of the simulator or hardware device. So basically, I know it's a thing that is tempting for folks to do, try to allocate qubits in one fragment of quantum code, and then return them to classical code to be used later. This is not something we support. So basically, a Q# program is something you run on one run of your quantum device. And if you're running on a quantum device, you're not going to be able to store the state of your qubits in a JSON object. You need to basically perform your computation, give the device the instructions, the gates, and then perform measurements, because you just don't have the access to the internal state of the qubits to be able to convert them into a file. So this is not supported kind of natively. Now, that being said, Q# allows you to define your own simulators and also extensions of simulators. For example, the quantum katas use a lot of counter simulator, which is exactly like the full state simulator, but it also counts how many gates of different types you did. It uses it to check whether your solution is correct or not in some of the tasks. So that is a custom simulator. So if you really want your qubit state as a JSON object, you can write a custom simulator that will expose a custom operation that will basically dump the state of your quantum system into a file, into whatever format you want. And then you can have another operation that reads that file and I guess figures out how to prepare that state on your system, actually using the library operation that I just showed you. So it is possible to do. It is not done natively or naturally. It's quite a lot of a hack. But if you really need this to happen, you can make it happen.
Well, thank you. There's one more question. One of our viewers is wondering, do you have to be familiar with topological quantum in order to use Microsoft Azure Quantum?
Absolutely not. That's my favorite part about quantum programming. You don't actually have to know how the underlying devices work. You don't need to know physics to figure out how to write programs. So if you look at Q# code a little closer, for example, where do we apply any gates? So here, for example, we allocate a qubit and we apply gates to it. And nothing in this code tells you what is the physics behind those qubits. Like, you cannot tell from the code whether it's going to run on a simulator in which they're not actually physical objects, but rather software arrays of floating point numbers, or whether they are topological qubits, or whether they are trapped ions. This is just not something that Q# expresses in the code. Now, the Q# compiler and runtime has a lot of layers in it that it uses to convert the Q# program into something that can be fed to the quantum device as instructions. So this kind of information about the actual quantum device on which the program is running and how to convert the logical instructions to the physical ones running on that device. That's done on the lower levels of runtime that are specific to the specific provider. But as a software engineer, you don't write that level of instructions. You write the high-level programming language. And I think it's not just Q#. I think Qiskit doesn't also include the actual physics in Qiskit programs. Like the core Qiskit, at least from what I've seen from it.
Another viewer is wondering, can you save snapshots of the quantum state, for example, by using a counter simulator?
If you want to get a snapshot of the quantum state without kind of doing anything else with it, just for looking at it, you can do it even with the normal full state simulator. The dump machine operation that I showed in yesterday's talk does that for you. It doesn't run if you run it on quantum device, but if you run it on a simulator, it effectively prints for you a snapshot of the quantum state without performing any measurements or modifying the state in any way. So it just prints the state. And you can actually print it to a file. So you can have several snapshots from different points of time in your program execution.
The last question for now is about how quantum decoherence is measured. So can you measure quantum decoherence through feedback loops in a classical circuit?
I don't actually know the answer to this question.
That's totally fine. That should be all for the questions for now, so you're free to continue.
Good. Then let's take a look at one last piece here for now. How to write unit tests for the quantum code. Here I'm writing unit tests for the non-standard part of this algorithm, so the quantum oracle. And here I want to check that my quantum oracle, this check whether the integer is a solution to the modular equation, actually implements this function. So what I'm doing here, I'm using a helper operation that takes a classical function as a parameter and the marking oracle, and checks that this marking oracle produces the same results as the classical function on all inputs. So I iterate over all possible inputs, prepare them as input states, apply the marking oracles to them, and check that the result matches the result of evaluation of the classical function. And then I also check that the inputs were not modified, because that's two components of quantum oracle. You need to get the right result and you need to preserve your inputs. And since we know that if the quantum oracle doesn't do any measurements, its effect is defined by its effect on the basis states, which is supposed to be defined by the classical function it implements. So if it matches the result on each on each input state, then it's correct. And here is a classical function that performs the same check, but much, much shorter. And then this operation is the actual unit test. Any operation that is annotated with @test is exposed to the XUnit testing framework as a test. And its parameter tells us what is the simulator on which this test needs to be run. Again, we're using the full state simulator here. And inside the test, we have a bunch of test cases. And we check that for each of those equations, the quantum oracle implements the corresponding classical function. And then in Test Explorer, since Visual Studio Test Explorer picks up XUnit tests, you can see that they are recognized here as unit tests, and they pass. Any questions about this little piece?
There are no questions in the chat currently.
Okay, good. Then we can go to the next step and take a quick look at how you can run the steps 4 and 5 from Q# Jupyter Notebook. It repeats a bit of yesterday's demo, but with this Grover search demo rather than yesterday's Deutsch algorithm. So this is a Q# notebook. You can see that it's Q# kernel. And various percent something magics expose different simulators and tools to the user. You see that here in the Jupyter Notebook, I don't have the actual Q# code. This Jupyter Notebook, if you look at the GitHub repository, lives in the same folder as the Q# code that I just showed you, the library Q# code. So it has access to all operations defined in there. You can think of it as the Q# project being the backend and the Jupyter Notebook being the front end. So you don't need to copy all the code here. You can just rely on it picking it up from the file. That's actually what I do often when I work on projects. I develop them in Visual Studio, and test them in Visual Studio. And then I use the Jupyter notebooks to do things like visualizations and, of course, demos. So here I call the same full state simulator for the same code find equation solution, but with simpler parameters than the ones I used for Nielsen and Chuang ISBN. This is me basically preparing to run code on a quantum hardware. So you see that the equation is much simpler. We know that the answer should be x equal 2. And the result is two measurement results, 0, 1. By default, Q# stores integers in little endian notation. So the most significant bit is stored last. So it's actually 1 multiplied by 2 plus 0 multiplied by 1. So x equal 2, indeed. Big success. Now, let's do the fifth step of our workflow. Figure out how many resources are required to run this solution in terms of number of qubits and number of gates. You can see that it has quite a number of parameters. The ones we care about most are the widths, which is the maximum number of qubits you need to run this program, and the C0 count, which is very roughly the measure of the depth of the circuit and its complexity. You see that width is sort of reasonable. 8 qubits is not too much. But the number of gates and the depth of the circuit are quite big, actually. 1500 C0 gates. It means that if we try to run it on hardware, it most likely won't give us a useful result. Now, actually, a question I got last week, a good one, asked why are we talking here about the C0 gates if we are preparing to run this code on IonQ device, and IonQ device doesn't have C0 gates as the built-in ones. The native gate set there is different. Now, this percent estimate magic is the general purpose resource estimator. It performs statistic counting not applied to a specific device, but rather general gate complexity of the circuit. It would be possible to figure out how many gates exactly it takes on an IonQ device, but for that we would need a tool implemented in the runtime of IonQ devices that knows exactly the layout of the device, the native gates for it, the logic that is used to compile the circuit into what goes into actual device. We don't have that, so instead we use this general purpose resource estimator. It allows us to do some nice things, like, for example, optimize our code to see where are the fragments that take the most complexity, and maybe rewrite them. And since we have our unit tests, we can rewrite the code that we don't like for its complexity into something simpler, while still checking that it is correct. So let's take a look at what our circuit looks like. %trace command prints the circuit produced by the operation from one run of this operation. And you can see that it is a long circuit with a lot of controlled rotations. Yeah, a lot of controlled rotations. We probably don't want to run something that is that complicated. And then if we reduce the default depth of this circuit. You see where this complexity comes from. Basically, each of these blocks is clickable. You can click on this block that represents an operation to figure out what are the pieces that go inside it. So you see that multiply by modular integer and increment by modular integer are the library operations I used in the code, as well as prepare arbitrary state. If you drill down into a specific operation, you can see what it consists of. For example, if we look at approximately prepare arbitrary state, it has quite some levels of nesting, but you see that we go into more and more complicated library functions with some parameters. And you can do the same for any of the blocks. So if we do some of this analysis, we can see that there are two main sources of the complexity. One is this modular arithmetic, modular multiplication and increments. And the other one is this state preparation. So let's go back to our project and rewrite our code to simplify it. Here I'm going to rewrite it for one very specific case. Well, 4 very specific cases, strictly speaking. But what I'm doing here, I dropped the parameters A and C. I fixed them to remove modular multiplication altogether and to fix the modulo C to 4. So now our modular equation uses only addition, and it is addition modulo 4. And addition modulo 4 is really nice. You can write a ripple carry adder for addition very easily. So this is what we do here. We do increment for the lower bit and for the higher bit independently. And this kind of logic is going to be much, much more simple than the full-blown modular computations, because it's just an X gate and a controlled X gate. So like 7 gates total. And another simplification we do is we use a more efficient state preparation routine. Since we know that we're going to be preparing a superposition of all basis states this time, well, we're going to just apply Hadamard gate to each qubit, save ourselves a lot of those arbitrary rotations. And then, of course, we can have a unit test to test the simplified logic to make sure that it is correct, again, for all possible inputs of the parameter B. So this way we can convince ourselves that the logic is still correct, even though we modified the code quite a lot. And now, if we go back to this Jupyter notebook, we can run the simulation for the parameter we want, again, to convince ourselves that the result is the same we had, and it is. And then we can print the circuit. Let me switch this back. We can print the circuit and estimate its resources for the simplified solution. And you can see that this circuit is much more reasonable. In fact, the compiler is going to simplify out a lot of it. For example, those 2 X gates are going to cancel out. Those 2 X gates are going to cancel out. So it's going to be much easier and much shorter in the end. And here are our source estimation values. For now, we can see that we only use 3 qubits instead of 8. which is a big improvement. And our CNOT count is actually double digits. So we got a 2 order of magnitude improvement over what we had with our high-level library solution. This is the trade-off we have to do sometimes, given that we are in the era of NISQ devices. Sometimes our programming tools and our libraries are too advanced for what we can do with the current hardware. So we can write simple and convenient quantum code using the libraries, but then sometimes we have to go back and see how we can tweak it so that we can actually run this code on hardware devices. Okay, this is the next logical break in the demos. After this, we're going to go to the second part, the Azure Quantum job submission. Any questions so far?
Yes. The first question from viewer is, maybe I missed it, but how do you calculate expectation values in katas? And is it straightforward?
Expectation values of what?
Expectation values in the quantum katas. So I guess just mean he meant in Q# more generally. How do you calculate expectation values?
Now I'm trying to remember where in the quantum katas I do compute expectation values. I think kind of the regular way, run the program multiple times and add up the results and divide. There is a library function that allows you to do a shortcut for computing expectation values when running on a simulator. It's called estimate frequencies. So basically, instead of running the simulation multiple times and averaging the results, it actually runs the program once and then computes expectation results from the state vector. But it's a hack, it's not going to work on hardware. In the katas, I'm not sure I compute a lot of expectation values. I try to make my testing harnesses deterministic. So for example, when there is a task that requires to generate a random number, I kind of don't have a way around it. I have to run it multiple times and gather some statistics about it. But for example, if if the task asks to prepare a quantum state, I don't actually need to find any expectations. I can check whether the state matches the expected one by applying the operation that prepares this state and then applying the adjoint of the correct solution. If these two solutions prepare the same state, the result's going to be the cat 0 state. And there is a library function that allows to check whether the state is cat state. But it doesn't rely on computing expectations.
Okay, so the next question is, how are oracles and operations lexically scoped if null operations are measured via basis state change?
How are operations and functions lexically scoped? From the code organization point of view, the code is organized in namespaces. So all operations are visible within its namespace. And then you can open namespaces to get access to operations from other ones. Like here, I'm opening a lot of library namespaces to get access to the operations defined there. Did that answer the question?
I believe so, thank you. Another question in the chat asks, can the CNOT gates be classical such that the nodes are being sorted? The nodes being sorted can be measured for complexity, and does this aid in fault tolerance?
You folks are asking better questions that I'm prepared to deal with. Yeah, I don't think I have a good question for this, a good answer for this one.
That's totally okay. Okay, it seems that we should be good for now on questions, so you can continue again.
Okay, sounds good. Now let's go to the juicy part of it. And wow, it looks like we might actually take the better part of the 2 hours that we allocated for this workshop. Okay, let's see. The next step we want to do is, now that we actually tweaked our code so that it's going to run on hardware, to actually run it on hardware. To do this, we are going to use Azure Quantum. And I'm going to show you 2 demos and 1 video. For my first trick, I'm going to show you how to submit this program to Azure Quantum. Here is what a quantum workspace looks like. When you get access to the Qiskit workspace, if you choose to work on Microsoft Challenge, and this is going to be its landing page. Let me make the font a little bit bigger. The landing page has information on the parameters you need to connect to the workspace, such as the subscription ID and resource group and storage account. It has things like job activity, which shows you that on April 4th, I did some job running, well, preparing for today's workshop. There is a job management tab that shows you the history of the jobs I ran. And well, that's for the demo. That's going to be the second one today. And there is a place to run hosted notebooks. Basically a way to run quantum programs from notebook environment without having the local setup for them. We will return here a little later for our second demo, but for my demo right now, I'm going to use my local setup. Also, I'm still going to use Jupyter notebooks. They allow to build histograms, and I just cannot resist the temptation. So here I'm using now a Python notebook. I showed you yesterday in the workshop how to submit Q# jobs from a Q# notebook. And there are so many environments available, I need to diversify my tricks. So now I'm using a Python frontend to integrate with the same Q# code and to both integrate it with the classical compute and to submit quantum jobs to Azure Quantum. So we start by loading the right libraries, modules that enable Python to Q# integration, and the operations implemented by the C# code. Next, let's run the same simulation from Python, just to convince you that it's still the same simulation. We're going to go right straight to the simplified solution code. And when you integrate C# with Python, the syntax is a tiny bit different. The operations are still exposed as Python methods, but instead of passing the right simulator as a parameter, you're going to use one of the methods that corresponds to the simulator. For full state simulation, it's .simulate method. And then you pass parameters to it as normal method parameters. And here is also a bit of classical integration, the conversion from little endian bit notation to an integer. So here we're running the simulation, print the measurement results, and convert them to an integer right away. The same thing we did when integrating with C#. We still got our result. Now let's run the result estimation here. It's again the same result we just got from Jupyter Notebook, 11 CNOTs, 3 qubits. But here it was obtained by using estimate resources method. You can do that from Python as well. And IonQ system has 11 qubits, so we are good to go with this program. The next step is connecting to Azure Quantum. Here you see that the method Q# Azure Connect requires you those parameters, subscription, resource group, workspace, and location, that were shown on the landing page of the Quantum workspace. When I run this cell, if I run it for the first time in the past 12 hours or so, it asks me for this kind of extra authentication, but I just did it before the workshop and it should be still good. Once we do this Azure Connect logic, it reports that it connected to the workspace, and it gives you the list of all targets available in that workspace. Here, I'm going to use the IonQ targets, which you can see are to the simulator. That is a perfect simulation, the same as the full state simulation used by C# QDK, and QPU, the quantum device. And it also reports you the average Q time in seconds. There are also Honeywell targets, and actually you can see that it is a pretty old namespace, workspace, because it still calls Honeywell targets Honeywell. In the newer ones, in the demo I'm going to show you second, it's already updated to Quantinuum. So if you create a workspace today, it's going to say Quantinuum. So we have connected to the workspace. The next thing to do is to choose the target in this workspace. I'm going to start with the simulator. As I mentioned before, always a good idea to start with the simulator. It loaded the package necessary to do the job submission for IonQ and reminds us of the queue time very fast. So here I'm going to submit a job. Now any jobs I submit using qsharp.azure.submit are going to go to these targets that we selected here. And when I do job submission, I pass the operation name, any parameters it has, the job name, just for convenient readability, and the number of shots. As a number of shots tells us how many times to run the program to aggregate its results and return them as a histogram. Now for IonQ simulator specifically, the number of shots is not used because IonQ simulator, if you dig in the documentation, always returns you the perfect histogram of the results rather than doing shots and then measurements and then aggregating them. I actually got this question a couple of weeks ago. Somebody asked, I'm running a program on IonQ simulator for a single shot, a random number generation program, and I still get both outcomes. How come? Which, of course, if you do simulation, measurement, and then aggregating results, you're not going to get two different results if you're running it for one shot. But if you are using IonQ simulator, it's going to give you the histogram rather than aggregation of shots. Okay, let's see what our job status is. It succeeded. Simulator jobs are very fast. It shows you the target where it ran and the creation time and when it completed. You can see that it was like 30 seconds, 35, something like this. And now we can fetch job results using the job ID of this job. So Q# Azure.submit returns us a job object, and it has a field ID, and then we can use Azure output and Azure status with job ID as the key. So we see that here this Grover search is a perfect one. It always gives us the correct result because we're looking for one state out of 4. So our histogram consists of exactly one element. And if we plot it in a histogram, it's not going to be a very interesting one, just a rectangle. And then we can write a little post-processing logic to get the most frequent key in the histogram, which here is going to be, again, our favorite answer, x = 2. Now let's see one more way to get the solution for this exciting modular equation and to confirm that it is indeed 2. Let's see how we do it in the QPU. Now, switching to the QPU is just as simple as selecting a different target. And it has a shockingly low queue time. It was higher on the weekend when I was preparing this demo, which is odd. But after this, the job submission code looks exactly the same. I could run the previous cell instead of creating a new one. And here I'm going to actually fetch the results of an old job that I submitted in the past, which does exactly the same code, but we don't have to wait for the results. You see that here the job status says that it ran on IonQ QPU. And at that point, it took something like 2 minutes from job creation to job completion. Now let's fetch the output of this job. And here we see that it's no longer just one value. Now we have an aggregation of all possible outcomes. The correct one that corresponds to x = 2 has still the highest probability, but now it's not 100% probability. Now it's 87% probability. And we have 3 other results with something like 4 or 5% probability. And when we plot this histogram, well, now it's a proper histogram. It shows us the most frequent value, but also the other values. Those other values are results of noise. So you can see that we used a pretty shallow circuit, and the compiler probably optimized it to be even more shallow. But still, the noise starts to affect our results. So this is something you have to keep in mind. You cannot experiment with circuits that are too deep. Otherwise, you won't get a useful result. It's going to be taken over by noise. But here we still got our result. We confirmed that 2 + 2 = 4. But most importantly, we did this using Azure Quantum and IonQ device. For my next demo, I'm going to switch the environment, the programming language, and the hardware device. Well, provider, just to give some variety. Any questions about this demo?
We have a question. So a user said, complexity varies for a number of states defined in Hilbert space for each snapshot. So can expectation values be used as a covariant to the total number of sessions necessary to define a discretized simulation given enough time to compilation? Yeah, and I'm sorry, this is not directly related to the demo just now.
Yeah, that sounds like another question for which I don't have a good answer.
No worries. Thank you.
Sure. I mean, it's better to admit than to bluff my way through it. Okay, let's see my next demo. And this one actually is a little bit of adventure. It's the first time I'm showing it. What can I say? I like to live dangerously. So let's take a look at how to run a Qiskit job on Azure Quantum, because that's something we saw a lot in our past hackathon. A lot of folks chose Qiskit as their programming language. So let's see how to do it. And to showcase both of our amazing hardware providers, we are going to do this on Quantum targets. So here, if you go to the Notebooks tab in the Quantum workspace, it's going to start you with a sample gallery. These are samples that walk you step by step, pretty much through very similar tools and submission process, as I showed you right now for Python and C#. In fact, this Jupyter notebook uses IPython kernel and C# programming language. It's going to look very similar to the steps I showed to you right now. You can use these notebooks to get started. Basically, they give you the framework of the steps you need to perform to run a job. So you just need to change the connection information, and I think it's going to be automatically substituted for you. And the code you want to write. So here, okay, let me collapse this. So you copy the notebook to your notebooks, and then you can work with it. Here, I already copied this one, Qiskit with Quantum. So let's see what it looks like. Okay. And let me go a little full screen here so that we have a slightly larger workspace. Oops, what was that? I don't know what happened. So the logic is very similar. We start by connecting to a specific provider, executing this cell. Now, the logic is very similar. You do the same steps, but what it looks like is going to be different. Here, when we connected to the Azure Quantum workspace, we got the list of targets immediately. Here, we're going to need to print the providers manually. You see that there are targets both from IonQ and from Quantum. And you see that it actually is called Quantum, so it's a pretty new workspace. It's something like a recalled. Now, this notebook walks you through the possible values of targets. For Quantum targets, there are 3 types of them. There is API validator, there is quantum simulator, and there is the actual hardware. The API validator basically checks that yes, your program is going to be possible to run, and it's free. The emulator is effectively the noisy quantum simulator. Unlike IonQ's one, that is a perfect simulation, Quantinuum emulator performs noisy simulation, so it works very hard at simulating the actual noise from the quantum device. And then there is the quantum device. Depending on which target you choose, your job goes to that target. Now, next we create a circuit program, a Qiskit program that's going to run on your job. We're doing a very simple one, a single qubit random generation. And you can print the circuit using normal Qiskit tools that shows you what it's going to do. Next step, we want to submit this program to the API validation. First, because it's free. Second, we want to make sure that it will actually run. So we use provider get backend command with this kind of string that ends with API val. And then we run the job using this backend.run this circuit. Let's execute this cell and see what happens. So it reports you back the job ID. And now you can use this job object described here to monitor the job and to get its result. So you see that the result is the job already executed, and you can plot the histogram. Now for the API validator, it's not trying to simulate anything for you. Instead, it just succeeds if your job is going to run successfully on an emulator or hardware device. So it returns the all zeros value, and that's a kind of the expected behavior. Now, the next thing we can do is we can estimate the cost here. This cost estimation is different from the resource estimation that I showed you. It basically estimates the cost of the program in the credits that are used to basically to define how much the jobs cost. So this workspace that you will be using on Saturday is going to have a certain amount of credits allocated, and each job is going to cost credits, but it's not going to cost you. It's something we provide you as the resource. This is actually where the example notebook ends, but I wanted to run this job on an emulator as well. So I took advantage that the credits are already in this workspace, and I changed the backend here. I'm not going to run this now. I'm going to do the same trick of extracting the job using its ID. So here it's the target that ends with sim rather than API val. So it's going to run on an emulator. And here I can get the job based on its job ID, and then I can plot its results from the past execution. And here you see that we actually got our random number generated results. We get both 0 and 1, unlike our API validation that returned us always a 0. So this is a successfully executed job on Honeywell Quantinuum device. Not the device, come on, emulator. And here, after that, I also tried to submit a job to hardware, and I have a job ID here. But if we go to job management, you see that there is a new job to API validation that I just ran right now. But that my hardware job is still in the queue. And it's been there for about 2 hours now. So I don't think it's going to finish by the end of the workshop. Okay, this is it for my second demo, Qiskit with Quantina. And now the last thing I can show you is a short video by one of my teammates, Gwen. It is a little outdated, so that some of the interface elements don't look exactly like they look right now. But it shows you how to run a job from Cirq, and it shows you how to run a Qiskit job, taking an existing source, a notebook in that case, and modifying it a little bit to run on Azure. So let's take a couple minutes for this video, and please interrupt me if the sound doesn't come in. It should. Let's welcome Gwen in recording.
Hello, my name is Gwen Perwira Mojo, and in this demo I'm going to show you how to submit quantum circuits using Qiskit and Cirq to your quantum workspace in Microsoft Azure. So to get started, I'm going to download this Jupyter notebook here from a sample in the Qiskit textbook called Estimating Pi using Quantum Phase Estimation Algorithm. I'm going to then replace the lines where this notebook connects to the IBM Quantum Experience so that instead it runs it on Azure Quantum, and then I will run this against the IonQ simulator. So let's download this notebook. Then I can go back to my Azure portal, open my Quantum Workspace, and for this demo I'm going to use the Jupyter notebooks that is built in to the Azure Quantum Experience. If you would like access for this, you can request that through our early access program. So here I've downloaded and uploaded this notebook already. Just going to minimize this. And as you can see, it's just the entire sample that we just saw on the other web page, the other tab here. It's identical. So to get started, I'm going to need to install some dependencies. So this notebook uses Seaborn, which I need to install. And then we also need to install Azure Quantum using the Qiskit optional dependencies. Oh, there we go. All right, so now we can scroll down to the piece where it connects to the IBM Quantum Experience and comment that all out. It's just these two cells here, and create a new cell, and then I want to import from azure.quantum.qiskit, import the Azure Quantum provider, and then create a new provider. And here I'm going to use this really handy workspace snippet that's auto-generated. And I'm going to just delete this part here. The Azure Quantum provider takes the exact same input arguments as the workspace. So here we go. Now it's connected to the provider. So now I'm going to get the IonQ simulator backend. You can see that returns the simulator. And now I can just go ahead and run the entire notebook. What this does is, yeah, it just runs the sample against this simulator. So we commented out this simulator, so it's going to run it on this simulator instead. So let's scroll down a bit. There we go. So now it's running all the different jobs. And as you can see, The closer we get to 12 qubits, the closer we get to pi. And then here we can plot the results. So here we have it. We take an existing Qiskit sample, replace a few lines of code, run it against the Azure Quantum Service. So now I'm going to switch gears and do something very similar for Cirq, which is Google's Python package for creating quantum circuits. You can find this tutorial on the official Cirq documentation. If you go to quantumai.google.com/Cirq/tutorial/Azure Quantum, you'll find a few getting started tutorials, and then this time I'm going to show you getting started with IonQ and Cirq. So we can run this in Google Colab, and I've already gotten started on this notebook. So to install dependencies here, instead of the Cirq, the Qiskit optional dependencies, we use Cirq. So pip install Azure Quantum and then square bracket Cirq. It's going to install the Azure Quantum package with the optional Cirq dependencies. And then we can connect to the workspace. So I previously showed you that automated snippet that gets you the subscription, resource ID, location, etc. You can also just copy only the resource ID and the location, and that will also get you the connection to the Azure Quantum Service. So here, this is what the import looks like from azure.quantum.cirq, import Azure Quantum Service, create a service object. So it looks all pretty similar to the previous workflow, except that now it's called Azure Quantum Service. And here we can actually specify default target. So if you connect to the service, we can actually by default submit jobs to the simulator. Then service.targets lets you list all of the targets that are available in the workspace. And here I've provided the provider ID for IonQ. And this will prompt you to authenticate. So you have to go to this website and then enter this code, and it will log you into your Azure account. And as you can see, we have access to the QPU and the simulator. So now we're going to go ahead and run a simple circuit. So you run a circuit that contains a square root of x gate, which is a native gate to the IonQ system. And then all we need to do is take that service object and run service.run and pass the circuit here as the program input parameter. Here I've specified 100 repetitions. And this returns a Cirq result object, which basically gives you a bit string where each character in the string is the result of a single shot. So since we use 2 qubits, qubit 0 and 1, here you can see the 2 bit strings each have 100 characters. And then we can go ahead and run this on the QPU. This will take a bit longer to run since the queue is a little bit longer. But basically it's the same idea. You use service.run, then pass in the circuit, the number of repetitions. And here, since in the previous cells I've used the default targets, which was set to the IonQ simulator, now if we specify the IonQ QPU target, it will actually submit this job to the QPU. So we'll let this run, and I want to quickly show you how that shows up in the Azure Quantum Workspace. So if you go back to your portal.azure.com and go to your workspace, there's this tab here, Job Management. And there we go. This will actually show you the jobs we ran. So here you see I just submitted a Cirq job. This is my job ID to the QPU target, and it's still waiting. So it's waiting to be run on the QPU, waiting to get its turn in the queue. And yeah, we can monitor it either here or in the notebook, and then we can fetch the results. We fast forward a bit, and the job has now succeeded. So if we now go back to the notebook, you can see this succeeded, and I can just print the result, and this gives me a similar data structure as the simulator. So if we want to do something a little different, and let's say the service actually times out because the job queue is too long, what you can do is actually go back into this job management tab over here, copy the unique identifier for the job. So if you can see the job succeeded and you want to fetch the results, then you can go back into the notebook here and then fetch the results like this. So I can get job service.getJob, and then here copy paste that job ID, and then this will also give me the job back. So here I can use job.results.toCirq result, and we can put this in a print statement. And again, this will give me the exact same data structure and the same result. So there you have it. Those are two different ways of fetching your job results with Cirq, with the Cirq support for Azure Quantum. And that concludes my demo. Thank you so much for your attention, and I hope you enjoy the rest of the conference.
Okay. This is the last demo I wanted to share with you. You can see that in all programming languages and all hardware providers, the logic of job management is the same. You pick the provider, you pick the target, you submit the job, you wait for it to complete, you fetch the results. But the details depend on the actual language and environment you're using. This is all I had for you today, so let's give the last chance for the questions, and we'll be good to go.
Thank you so much, Maria, for presenting today. I'll give 1 more minute in the chat to see if any more questions arise, but right now there are no questions.
Sounds good. In this case, while we are waiting, let me remind you that all the details we can share right now about our challenge can be found in this, oh, come on, in this blog post. And I expect to see you in some more events on Thursday and Friday, and then on our hacking time on Saturday. The instructions for the challenge itself are going to be published on Saturday morning alongside other challenges. And I think I actually successfully avoided giving too many spoilers. And the instructions for getting access to the Azure Quantum Workspace are going to be shared probably around Friday. You will need to create an Azure account, either as a student or as a professional. I think the difference is whether you need to provide a credit card or not. Or if you don't want to create one, you can team up with somebody who created it. You don't need more than one account per team. Also, it can be convenient for multiple people to be experimenting at the same time. I know I have multiple accounts myself, you know, one account per demo. Not quite that, but 2 accounts.
Great. Thank you so much, Maria. Yeah, there are no further questions in the chat. So I think we'll wrap it up here. Yeah, Maria, I really enjoyed your demonstrations today, and also for showing video by Gwen. And for the viewers, if you have any lingering questions, please post them in the Discord channel under Microsoft, and the recording will be made later on Twitch.
Thanks so much again for everyone who showed up today, and we'll see you all at the next event.
Have a great rest of the hackathon.